Hello everyone. In this video we are going to look at bolted joints that are under external force or pressure, and we want to answer this question that how much of torque do you need to fasten these bolts with so that it can keep the members together with no leakage of, let's say, that gas or whatever it is under pressure, and also these bolts don't fail, right? We don't break them, because we know if we tighten these bolts too much, they're gonna break, and if we tighten them not enough, then there will be leakage. So how much of torque do we need? And to answer that, we need to learn a bunch of things. So first is, we need to define for the bolt a spring constant. We know if we tighten the bolts will be under tension, they're going to be stretched, and the members that are attached together will be under compression. And you know from solid mechanics that if you have any material, let me see if I can move this. If you have any simple material with a constant cross section and with a length given, so let's say here we draw this member, and this member is exposed to force F, and the cross section is A, and the length is L, and the Young modulus is E. The elongation delta will be F times L over A times E. And if this is equivalent to a spring with a spring constant K, if these two are equivalent of each other, then the elongation is going to be simply F over K. And if you simplify the F from both sides and take a reciprocal, you see K is going to be AE over L, which is exactly this formula that you can see here. So now why do we have two Ks here for the bolts? Well, the problem is your bolts are not typically threaded all the way to the top, and only a portion of the length of the bolt is threaded. We show it by LT, and the rest of it, which show LD, is not threaded. The diameter of the unthreaded part is D, but the part that is threaded, diameter in it changes from the nominal diameter D, right, to some minimum diameter. And so the cross section of the threaded part also varies. So we cannot simply use the same cross section that we use for the unthreaded part. We need a separate cross section, which here we show it by AT, right? This AD here, this guy is simply pi d squared over 4, but not AT. AT, we call it the tensile stress cross section. And for that, based on the type of the bolt, we have tables that give you that cross section. So here is a table for metric bolts. So let's say if you have an M10 by 1.5 bolt, then you go and under this column here, you can find that the tensile area is what? 61.2 millimeters squared. And there are similar tables for the bolts that are in the inch system, SAE bolts. So here we can calculate our AD and AT, and of course the bolt is entirely made of the same material, so there is one Young modulus, and there is LD and LT, so we find KD and KT. These are the spring constants for each part of the bolt. Now if you look here, you see that these two parts, the threaded and unthreaded parts, are in series, right? You see there is one spring here and there is another spring here. So this guy is KD and this is what? KT. And you know the equivalent of two springs in series is what? The formula for it is the sum of the reciprocals added and then take the reciprocal. If you do that for these two Ks, this is the total spring of the bolt, okay? So now that we found how to find the spring constant for the bolt, you might say, what about these two materials that are clamped together by the bolts, right? So here I have these two pieces of material, metal, wood, whatever it is, clamped together. And also in between the bolt and nut, you might also have what? Washers. And we need to also determine a constant for this entire set of objects that are between the bolt and nut and they are under compression. We need to determine a spring constant for that one as well, which I'll show you. We call it Km, and I'll tell you how to determine that. Then once you have Kb and Km, then we can say, if you look at this picture, we can say that there are these two surfaces, one here and one here, and between them there is what? There is a Kb and there is a what? Km, like that. And they are exposed to the external force P. And then we determine how much of this P is applied to the bolt, how much of it is applied to the members, and then from those forces we determine how much of torque do we need, and make sure that the bolts also don't break. Okay, so we'll do that in a minute, but first I want to tell you how to determine the spring constant for these members. So there are different formulas in the literature, and one of them that is called the method of conical Frosta. It's one of the formulas that is commonly used. And in this method, basically, there are some parameters that you can see. One is the Young modulus, a common Young modulus, assuming that these two material being bolted together have the same material. These two pieces have the same material, the same Young modulus. D is, of course, the diameter of the bolt, the nominal diameter. And we have L, which is the total grip length or the grip thickness here, which also includes the washers. Okay, so it's sum of the thickness of the two parts plus the thickness of the washers, as many as you have, 1, 2, as many. And this formula is an empirical formula that is determined, and the validity of that was approved by ultrasound measurements of the stress values. Okay, or you could use like finite element methods, and again, it's not a simple calculation. It's not as simple as, hey, I have two springs like the bolt in series and I find it. It's not as simple as that. Typically, if I want to just very briefly just mention, they found that under this washer there is an area of compression, there is an area of stress, which is like a cone like this, and it can go all the way up to here. And this top angle here, half of this top angle basically, let's see if I can draw a straight line. Half of this top angle, this guy here, is called angle alpha, and then alpha is most of the time is approximately 30 degrees. It depends on the size of the washer, the head, and everything. And based on the shape and size of that area, they determined basically a formula for this Km. Okay, so this is not a simple calculation and it's beyond the scope of this lecture, but if we follow this formula to calculate the spring constant for what? For the members. Now, let's see how we distribute the forces, this external force P, between the bolt and the members. And by the way, this P here is a force, okay? This is an external force, it's not a pressure. So keep that in mind. Now, how do we distribute the external force between members and the bolt? Well, here, if you look, the members and the member spring and the bolt spring are in parallel this time, not in series. So how do we distribute the load? Well, we know two formulas. One is that if one of them carries a force, call it Fm. So let's say this guy carries a force, call it Fm. And this one carries a force, call it Fb. We know that Fm plus Fb has to be equal to what? Has to be equal to P. The other thing is the deformation due to Fm in the spring Km and the deformation of Fb in Kb, they have to be equal because the two ends of them are the same point. So the same delta, the same elongation for both springs is equal to either Fm divided by Km, or it's equal to Fb divided by what? Kb. So from this one and this one, you can clearly see that Fb is going to be Kb over sum of the two K's times P, right? And Fm is going to be Km divided by the total K times P. Right? We know this simple distribution of forces among parallel springs. And this is what you can see down in these two formulas. You can see here the Fb is something times the P, and Fm is 1 minus that something, 1 minus that C times P. So these two are exactly those formulas. So the C, as you can see, is the ratio of the bolt spring constant over the total, which we call it the stiffness constant of the joint. So the bolt force is C times P, and the member force is 1 minus C times P. Okay? These are the forces in them as a result of the external force. Now you might say, what is this Fi here? What is this Fi doing? This Fi, we call it the preload or pretension. This is the force in the bolt and the member as a result of what? As a result of tightening the bolt, right? You know, when we attach these members together, we always apply some torque and we tighten them ahead of time. So the bolts will be under some tensile force and the members will be under what? Some compressive force. So this force Fi is due to tightening the bolts. And of course, you can see that the positive of that is added to the bolt because it applies a tension to the bolt. But negative of that is applied to the members because it applies a compression to what? To the members. So these two formulas will give you what? The total force in the bolts and in the members. Good. Now, we know the forces. Let's talk about safety factors. How do we make sure that the bolts don't fail? How do we make sure that there is no leakage, right? The members don't get separated. So first safety factor, N, we call it load factor for bolt failure. It is calculated by this formula, and you might say, what is this formula? Well, let me explain that. So if there was no preload, nothing, how much is the maximum force that a bolt can tolerate? Well, you know, force is always the strength or stress times area, right? So force is strength or stress times area. So this SP here is the strength of the bolt material, and this AT is that tensile stress area. So if I multiply these together, this is the maximum force that the bolt can tolerate. Now, out of this total force, the Fi part of it is already applied. It's already there because we tighten the bolts. This part is not under our control. This part is already taken and we cannot adjust it or change it. So we have to take this portion out, and the difference between these two is all we have under our what? Under our control. So this total thing, this total numerator, is all of what? Is all of the force that is allowed for us to apply to the bolt at max, considering that there is some preload. What is the CP? Remember, the CP is the portion of the load on the bolt as a result of the external force, right? So this is what? This is like F real. This is the real load that you're applying to the bolt, again, if you don't consider the preload. Right, so you see this safety factor is the maximum force that is under my control to change over what I'm really applying, and clearly the safety factor has to be what? Bigger than 1, so I assure that the bolts are not going to fail and break. That's one safety factor. The second safety factor is called the safety factor for joint separation. It is defined as Fi over P1 minus C. Where does this one come from? Well, here, what we need to look is this Fm and the formula for it. This is the force on the members. Good? Now, if the two members have to stick together and not have any leakage, then they should be under compression. So the members should always, the force in the members should always be negative, compressive. They should be pressed against each other. So the gas or whatever it is that we are trying to keep, or the force does not, the gas does not leak, or if there is a force, basically it can keep them and the members don't get separated. So this force should always be negative. When is it that these two members can be separated from each other, or what? Or the leakage can happen is when this Fm becomes what? Positive or zero. This should never what? Happen. If this happens, then the members can easily be separated without anything. Why? Because the tension in the members is more than the negative preload, and so the members now will be separated. So what does this condition mean? This means that 1 minus C times P minus Fi should not really be bigger than or equal 0. Now, if here I take the Fi to the other side, it becomes like this. And if I divide both sides by 1 minus Cp, then you see that Fi over 1 minus C times P is going to be less than or equal 1. So as long as this ratio is less than or equal 1, there will be separation of the joints. But if this ratio is bigger than 1, there will be no separation, and that's exactly what you see here. As long as this ratio is bigger than what? 1, then the members will not separate. Okay, so now, if I want to summarize these two safety factors and what we can get out of these two safety factors, let me briefly and fast tell you what do we get out of these safety factors. So here we choose a safety factor, let's say 2, 3, based on the application and the standards. What does that give us? Well, if P is given to me, if I know exactly how much load I need to tolerate, and if I have chosen my bolt and the members and the washer and everything, so I can calculate C, which we call it the stiffness constant of the joint. And if I calculate, I choose N, this will give me what? This will give me Fi. How much of preload do I need to avoid joint separation? How much preload force do I need to avoid joint separation? So this one will give me Fi. What does the top one give me? Well, in the top one, I already calculated Fi from the bottom one. I know Cp, and I choose N. Again, a safety factor for the bolts so they don't break. Then what I need to find is what? This guy here, Sp times At, which is the material and the geometry of the bolt. Now you might say, well, look, you said if you want to know everything except for SPAT or in the bottom one, you had to know C. C depends on KB and KM, especially KB, and KB means, if you know KB means you have selected your bolt, but guess what? Look here. You haven't selected your bolt apparently, because you say you have to select AT and SP. Right? So you see, that's what we have in the design. Design is typically not a straightforward calculation. It's a trial and error. You choose a bolt, you choose a C, you choose a bolt, you go forward, and then you'll see if you can get the design done. Otherwise, you come back and modify it, because some parameters will appear everywhere, like this C. So if I say, well, C is determined, and I can do nothing about C, and the bolt is selected, then I have to say what? My AT is already selected because the bolt is selected. Then the only thing I'm allowed to change in this design is SP, the material. So you consider a specific bolt design, and then here from this top one, you say what material the bolt should be from so it doesn't what fail. But typically, you are allowed to change both material and geometry, and it takes some optimization and trial and error before you get the best design. Okay, it's always a cycle, it's not a straightforward calculations. Okay, so now I'm sure my bolt is not going to fail, and I'm sure the members are not going to separate. So let's go and answer the initial question. How much torque do I need? If I use a torque meter, a torque wrench, how much torque should I see on the dial when I'm tightening the bolts? Let's say for this engine cylinder, right? This engine cylinder head bolts. How much torque do I need to apply? Well, if you go back to the lecture I had on power screws, which you can see it, it's just published like a few days ago. The torque that you need for a specific load F, I provided you with a formula, okay, for a torque under some load. And here we are going to use the same formula here with some modifications. Okay, here there is a little bit modification, but the essence of this formula is very similar to the one in the power screws. So here you can show that the torque that you need to tighten the bolts is a constant K, which we call it the torque coefficient, times the amount of preload that you calculated here, times the diameter of the bolt. Now, diameter is clear, the preload we calculated is clear. Let's explain this K, this torque coefficient. In that, there is a dm, which is the average diameter of the bolt. There is d, the nominal diameter. There is lambda, which is the lead angle. Remember this one here? That's this angle lambda, the tangent of which is L over pi dm. And there is F. Here, this F is that coefficient of friction. Is the same as mu that I explained. This alpha angle is this angle I told you, the angle of the cone, which typically a 30-degree angle is used. And finally, there is an extra term here. This is the friction between the head of the bolt and the washer. So this is the mu for washer and bolt, or bolt head. Why? Because if you look here, there are two places where friction exists. Where are they? One is here. Here's a different color. One is here. Here you have thread against what? Especially this bottom part of it, because here you don't necessarily have thread of the material, right? You have really like this part. There is this part here, that there is friction of metal on metal for thread against thread, and there is also friction here, where the head of the bolt is rubbed against the washer. So that second term is for here, for this part. So if I calculate that torque coefficient multiplied by the preload I calculated already by D, that tells me how much of torque I need in my wrench. Okay, so you see that calculating how much torque you need to fasten the bolt with is not a very simple task. And by the way, all of these calculations we have done is assuming that this force P is a static force. It is a static force. If this is a dynamic force, like in engine, then you have to do fatigue design. This design here is just a static design. Fatigue design is more complicated, and maybe I talk about it in a separate lecture. But here, you see, even under a static load P, still calculation of the amount of torque that you need is quite a bit complex, but I just wanted you to know about the process of it and how to go about it. So hopefully my video was useful to you, and I'll see you in the next lecture. Thank you.